Welcome back, students. This is now technically Wednesday the 18th. It actually, is it Wednesday the 18th, Mr. Shaw? Or is today Tuesday?
No, it's the 17th, Tuesday the 17th.
Oh, I don't even know what day it is. Mr. Schaff is here helping me, and I didn't mention this before, but one for him, you know me in tech, this wouldn't be happening, so I'm extremely appreciative of him taking his time to be up here with me to do this. I really, really appreciate that. And so anyway, like I said, I've kind of lost track of time. This is the due nows for Wednesday, March 18th, had we been in school. And so today we're going to be starting to look at colligative properties. So we've got a second assignment with solution stoichiometry, which we covered yesterday. And now one of the colligative properties is osmotic pressure. We're going to look at that. So anyway, your homework for today was to complete the solution. What is that? I don't know why that plus sign is there. Interesting. Well, I'll deal with that later. But anyway, I did not collect that one. However, the solution stoichiometry 2 assignment that you would have picked up today, I am collecting. And so that would be your homework for tomorrow. Again, I'm not actually collecting it, obviously, since we're not in school, but make sure you check your answers with the key that's posted so that when we do get back to school, I will be collecting that. I mentioned this yesterday. I'll mention it again today. Since this week is technically an extension of our spring break, I had assigned this mastering yesterday on the 17th, but and it would have been due this Friday the 20th. But I did open it on the 17th. But it will not be due until Friday, April 3rd. So I'm leaving that as it is because that's the way it would have been had we been in school. But in reality, that assignment is due on the 3rd. And it will say that in Canvas on the calendar if you click on that. So I think that's where we are there. So let's go to our notes. This is where we would have begun today. So there are several properties of solutions, of aqueous solutions, that only depend on the concentration of solute particles. It doesn't matter what the solute is. All it matters is how much of it is there in the solution. These types of properties are called colligative properties, and there are 4 of them. Vapor pressure, osmotic pressure, boiling point elevation, and freezing point depression. In calculations involving colligative properties, solution concentration is given in terms of molality. I think I mentioned this last week when our last lesson in Unit 10.1 involved molality as a means of calculating concentration. And I said we were going to make a return to it, and here it is. So in regards to colligative properties, mathematically, all of those changes in those properties are tied to solution concentration in molality. So I want to do, which is, remember, is the moles of your solute over the kilograms of the solvent. All right. And so I want to do a quick review of some molality calculations here, and then we'll move on to beginning the colligative properties. So let's see. Scoot this up a little bit. Here we go. All right, so first, this first example asks us to calculate the molality. Remember, molality is a small m as compared to molarity, which is a capital M. Also remember that that the small m is not only represents molality, but is also the unit of molality, which is molal. Just like the capital M is also the unit for molarity, which is then called molar. So remember that. So it contains 42.5 grams of HCl. So this is the mass of our solute. And again, with molality, remember we have M for molality and M for mass. So make sure you keep those straight. Dissolved in 725 mLs of water. So remember, water's a solvent quite often, probably 9 times out of 10. But and so when that's the case, getting from volume to kilograms for water is quite simple, because with water's density being 1.00 grams per ml, an ml of water and a gram of water are equivalent. And so converting from mLs to kilograms is essentially the same as converting grams to kilograms, which is just dividing by 1,000 or moving the decimal 3 to the left. So that would be 0.725 kilograms as stated there. So first things first, so remember molality is moles over kilograms. Well, we don't have moles yet of our solute, so we're going to need to do that first. So N is equal to M over MM, the relationship. Remember, first 2 steps of mass stoichiometry, which is the conversion of mass to moles, or the other way around. We have a shortcut equation for that, so we'll use that again. So the mass of our solute is 42.5. We need to know the molar mass of our solute, which for HCl is 36 grams per mole. So 42.5 over 36. And again, since this is an intermediate calculation, we're not going to do any rounding yet. So this would be 1.180555556 moles. No rounding. Then we're going to find the molality of the solution, which is N over kilograms. So we have our moles right there, over the kilograms of our solvent, which is 0.725. Now we will round to, according to the data, 3 sig figs, and that comes out to be 1.63 mole. Remember to use the small m as a unit, and so to label your answer as such. Remember, the m stands for both molality and the unit of molality, which is mole. Next one, very similar. So we're going to find the molality of a solution that contains 25.0 grams of sodium hydroxide dissolved in 275 mLs of water. So again, with water being the solvent, that needs to be in kilograms. And so with water having a density of 1 gram per ml, again, that's a very simple conversion. So it'd be 0.275 kilograms. I do want to point out this, though, as we did when we discussed molality back in Unit 10.1. If the solvent is not water, all right, if the solvent's not water, remember, water doesn't dissolve nonpolar things, nonpolar solids. So if we're using a nonpolar solvent like benzene or carbon tetrachloride or cyclohexane or some such thing like that, then we would need to have the density of that solvent to get us from volume to mass and then ultimately to kilograms. So keep that in the back of your mind. So here's the mass of our solute, and now we're ready to roll. So once again, we're going to find the moles first. So we have 25.0. Okay, a molar mass of sodium hydroxide. So hopefully you remember that sodium is a +1 ion, hydroxide is OH -1. So we're looking at a formula of NaOH, so 23, 16, and 1, which is 40 grams per mole. So 25.0 over 40. Again, not rounding that at all, 0.625 moles. Thankfully, it's not a long one like that. And then to find the molality, we had 0.625 moles over the kilograms of our solvent, water 0.275. And again, this one would also be rounded to 3 sig figs, 2.27 mole. Another quick review on concentration. Remember, just as in molarity, molality works the same way. The greater the value of M, all right, the more concentrated the solution is. This has 1.63 moles of solute in a kilogram of water. This has 2.27 moles of solute in a kilogram of water. So there are more particles of solute in this solution than there are this one, which makes this one more concentrated. Okay. All right, next page. And we'll do our last example of molality. I keep wanting to walk over there because that's where normally I always remember scrolled up the notes, but of course Mr. Schaff moved it over here so that we could see me better. And that was quite the ordeal. We had to he had to get up in the ceiling and move the cable and the Ethernet cable and all that business so that we can move my computer over here where the camera is so we can get a better view of the board. So thanks to him for that too. All right, so next example here. Here we're going to determine the mass of potassium chloride, which is our solute, would be required to prepare a 1.25 molal solution. So that's our concentration in molality that contains 575 mLs of water. So once again, water is our solvent here. And so the conversion to kilograms is fairly simple. 3 to the left, divide by 1,000, 0.575 kilograms. So here we're given the molality and the kilograms, so what's missing is the moles. So with this one, we're going to start with the molality equation. Oops, not that one, which is M equals moles over kilograms. So we have 1.25 equals N over 0.575. So we're going to solve for N, and so we can just put that over 1 and cross multiply. So N would be 1.25 times 0.575. And again, no rounding this one since we're not done calculating yet. 0.71875 moles. And so to find the mass, we're going to use the relationship between mass moles and molar mass, which again is we can use our shortcut little equation to allow us to do that conversion, that stoichiometry conversion. So we have N equals M over MM. So the number of moles we have, 0.71875, is equal to the mass over the molar mass of our solid. So our solute is potassium chloride. Hopefully you would recognize that would be KCl. K is 39, 1 chlorine 35, 74 grams per mole. So that would go there. So again, solve for M, just put that over 1 and cross multiply. So we have M equals 0.71875 times 24. And again, based on our original data, not including molar mass, of course, because that's a constant, our answer would need to be in 3 sig figs, and that comes out to be 53.2 grams of KCl. So, little review there on molality. In our next several lessons after today, we are going to be using it in our calculations involving colligative properties. So, we're going to begin our discussion of colligative properties today with the first two. Erase this. Oh, there I go again. Wrong place. I need to put a wall there, temporary, so I don't keep doing that. There we go. All right. Before I talk about vapor pressure, I want to explain to you the difference or make sure that you understand the difference between a dilute and a concentrated solution. All right. So let's say we have a container, an enclosed container, and we have a given volume of water in that. All right. So this is pure water, our solvent. All right. I'm not going to draw all the particles. We can just assume they're there. All right. Now, if we add a solid to water and make a solution, but we don't add much solid, right? remember, a dilute solution we commonly call weak. So think about a weak glass of tea you've had, or a weak cup of coffee, or whatever. There's not a lot of solute in it. So let's say we make a solution, a weak one, a dilute one, that is the same volume as this pure water, only now it's got some solute in it. So it doesn't have a lot of solute, so I'll just draw a few particles in there. And then assume that all the rest of that volume is made up of water particles or water molecules. And then if we do the same thing, only now we make a concentrated solution. So think if you make a real strong batch of tea, all right, it's got a lot of tea particles in it. And so let's show that here. And again, and then fill it the rest of the way with water so that all these volumes are the same. But again, remember that all the other volume of this solution consists of water molecules. So the water molecules are there, I just didn't draw them. I want to focus on the solute. What I want you to understand from this is this. So when you have an enclosed container with a solvent in it, some of the solvent particles acquire enough energy to go into the gas phase, or they vaporize. When they do, there is a vapor pressure up here where these solvent particles have vaporized that creates a pressure inside the container, and we call that vapor pressure. Colligative property says this with regards to vapor pressure. The greater the concentration of solute particles in a solution, the lower the vapor pressure. They're inversely proportional. Here is why, all right? Keep in mind that these volumes are the same, okay? Here, all of this volume is taken up by water molecules. Here, a majority of the volume is still taken up by water molecules, but some of the volume is taken up by solute particles. And over here, the number of solute particles is significantly greater. And so the volume of water particles in here, water molecules, is reduced. So if these volumes are the same, this contains the least amount of water molecules. This has more, and this has the most. So right here, there is a lower concentration of pure solvent, water, in a solution of higher concentration. Just like we said, there's less water molecules in here per unit volume than there are here or here. Thus, you have fewer solvent molecules available to vaporize. And so vapor pressure is going to go down, okay? As we will soon calculate in the next several days, since vapor pressure is lowered by an increase in solute concentration, then the solution that forms when you add a solute to that water is going to remain a liquid over a larger temperature range, which in effect will lower its freezing point and raise its boiling point. So I want to show you this over here. Hopefully you can see it. Can they see this, Dave, from over here?
See, they should be.
Okay. So what I did here, so here is the range where water as a pure solvent is normally a liquid. Above 0 and less than 100, water is normally in the liquid phase. All right. You get greater than 100 or 100 or greater, of course, it boils, or 0 or below, it freezes. Now, when you add a solute to water and make a solution, what happens is these two temperatures extend. All right. They extend in both directions. So the boiling point goes higher and the freezing point goes lower. So a solution that contains water as a solvent boils at a higher temperature than water normally does, and it freezes at a temperature lower than what it normally does. That is very good to know, and we utilize that in a lot of things out there in real world land. We'll talk about some of those in the next couple of days. So bottom line is you increase the concentration of a solution, the vapor pressure decreases, all right? Because in an increased concentration situation, you have fewer water molecules that can then vaporize. Second thing is osmotic pressure. The movement of a solvent through a semi-permeable membrane from the side of lower solute concentration to higher is called osmosis. Mr. Schaff knows a whole lot more about this than I do, because I personally don't study that kind of stuff nor teach that kind of stuff. Not my thing. However, the chemistry involved with that is my thing. So you were to pick up a handout today, all right, this one right here. And we're going to talk about osmosis. Hopefully you remember what a semi-permeable membrane is. That's one that, as far as I think I know, is that allows certain things to pass through it and others not. Is that true, Mr. Shaw? That sound reasonable?
Yeah.
Good. So I'm not totally stupid when it comes to biology yet. So anyway, this occurs with water in all living cells and is vital to their survival. You know, we're 70% water, give or take, and our cells got to have water in them to survive. Not enough water or dehydration as compared, or whether the cells have not enough water or too much water, both are bad. It's going to affect the cell's ability to undergo its normal functions. And so osmosis is a critical process to cell survival. So osmotic pressure is the external pressure that must be applied to stop osmosis. So let's look at this diagram. So over here on the left side, if you look at this little U-shaped tube here, there is a semi-permeable membrane at the bottom of this U-shaped tube. And so on this side, we have a solution, all right? It says sucrose. So we have sugar dissolved in water over here, and on the right side, we have pure water, all right? And the volume levels are equal. Okay, well, here's the deal. It has to do with this right here. Over here, in this quantity of solution, there are fewer water molecules in there than there are over here, because even though the volumes look the same, this is all water molecules, and over here, some of that volume is taken up by solute particles, in this case, sugar. So we're looking at the same thing that we talked about right there. So since there is less water over here than there is over here, the water is going to move through that semi-permeable membrane over here. This is exactly what happens in your cells when you get a buildup of too much solute. All right, solutes are things like, you know, salt and other minerals that we take in with our food and our drinks and so forth. And so water is going to move into the cell as it would right here in this tube. So you see the result over here. All right. So as water is moved over here, even though these volumes are different, the volume of water molecules in both of them is the same, keeping in mind that some of this volume is taken up by solute particles, or sugar particles in this case. The greater amount of water that moves through that membrane, the greater amount of pressure that must be exerted to stop it, and that's what osmotic pressure is. And so, the greater the concentration of a solution, the greater the osmotic pressure of the solution. So these two are directly proportional, all right? The more solid you have in a solution, the more water is going, or the more osmosis, the amount of water is going to move through that membrane to equalize the amount of water on both sides of that membrane. And so the more water is moving, the more pressure it's going to take to stop it. So whereby vapor pressure and solution concentration are inversely proportional, Osmotic pressure and solution concentration are directly proportional. So those are our two first colligative properties. We have two more to go. The two that we have to go involve some calculations. So our lesson for today is over. So again, the assignment for today's lesson was a second assignment in solution concentration, in solution stoichiometry. And so that assignment, had you been here, would have been due tomorrow, and I was going to collect that one. So again, make sure you do that. Make sure that you check your work on the answer key page of my Canvas page, or the answer key link, I should say, to my Canvas homepage. And again, if you have any questions about what you're doing or what I've said in the lecture or whatever, feel free to email me, and I will help you with that. So this is Mr. Keister signing off for this lesson. I will catch you next time. Take care of yourselves.